you. So today I'm going to talk not about HRT799, but I will describe a work we did for another sex symbol in the community, which is Beta Pictoris b, the gas giant planet orbiting the massive star Beta Pictoris. So first let's start with a kind of small review of the results that has been obtained on the system. So Beta Pictoris is a well-known star. It has been studied now thoroughly for 29 years. It's a A6 type star, member of the Beta Pictoris moving group, so it has a well-known age. The star is well known to be an extended debris disk. And the debris disk rapidly reveals some peculiar features like asymmetries, so warp. The study also from Okamoto revealed several planetesimal belts. And also we found using high resolution spectra evidence for objects grazing the star and evaporating. So all these features were indicative of the presence of massive planets in the system disturbing the disk, and we, using NACO observations in the L' band in 2003, we discovered a point source in the midplane of the disk, so here. We monitored the point source a year later, in 2010, using still the same instrument, and we recovered it, but on the other side of the star. Then confirming that a gas giant planet was orbiting the star in the midplane of the disk. Since then, we have obtained a couple of new observations. So to confirm that the planet is in fact not orbiting exactly in the midplane of the main disk, but is tilted and is probably orbiting in the inclined inner disk in the system. We also have redetected the planet using other instruments and using different setups, so it's really a bona fide planet. So currently, just to make you a summary, we have observation in the L' band. This is mainly the discovery images, so at 3.8 microns. These observations they enable us to say that the object we were observing was having a mass around 8 to 9 Jupiter masses. We obtained new observations at 4.05 micron. With the APP on NACO, so these new observations, they enable us to derive the first color for the planet. So this color was used to put some constraints on the spectral type of the object and to confirm the mass of the planet. And then we obtained observations in the K-short band, so at 2.18 microns, and we redetected the planets. So it was in 2011. And this enabled us to derive the first crude estimate of the effective temperature of the object, which was around at this time 1,700 kelvins, but with, as you can see, a large error bar on the effective temperature. So we decided to pursue the monitoring of the planet, making new observations at different bands. So we obtained J, H, and M' band observations. So then extending the coverage of the observations from 1 to 5 micron. We obtained these observations with NACO using the pupil stabilized imaging mode, so angular differential imaging. Between December 2011 and December 2012, we used 2 different pipelines and 4 algorithms to reduce our data to be sure that we were able to find the planets, and also to be sure that there were no biases on the estimation of the photometry of the object. So as you can see here, this is our images at J band, H band, and M' band. So the planet is clearly detected with a signature noise between 8 to 23 sigma. We extracted the photometry using positive and negative artificial planets. And we used this photometry to first compare the photometry of Beta Pictoris to the photometry of well-known objects. So in particular, other young companions and some young L dwarfs identified by Kelly Cruz and Jackie Ferretti. And we found that the planets, the JHK band, colors and magnitudes of the planets are compatible with the picture that Beta Picturis is a early L-dwarf. And using this fact, we use bolometric corrections reported in the literature to derive a first estimate of the bolometric luminosity of the planet. We also try to play with the other colors. So actually the L' band and M' band colors are a bit peculiar, they are a bit red. So we don't really know what is the origin of the problem right now. So it might be a bias in the photometry, some excesses, or maybe some thick clouds. We also compared our photometry to atmospheric models. So actually we use 7 different sets of atmospheric models. They are all based on the Phoenix radiative transfer code. And they're unable to explore the different limiting case for the formation of dust in the atmosphere of the object. So all the models, they converge toward the same effective temperature. So we are fitting simultaneously the effective temperature, the surface gravity, and the dilution factor that enables us to go back to the radius of the object. And actually then we find a consistent effective temperature for the different models, but the models that incorporate dust in the atmosphere in the atmosphere are unable to better reproduce the whole set of photometric data points for the planets. We also found some insights for reduced surface gravity for the object, which is consistent with Beta Picturis B being a young object. And we combine also the effective temperature and the bolometric luminosity to derive an estimate of the radius of the planet, which is around 1.4 Jupiter radius. And this radius actually fits well with the predictions from the well-known hot start evolutionary models. We also derived some astrometry from our data. So this is this point here, which actually complements the current set of astrometric data points we collected on the system. So the first detection was made from data that were recorded in 2003, and we are now in 2012, so we have already a significant coverage of the orbit. And you can see that using these points as input as Monte Carlo simulations, we are already able to derive good constraints on the semi-major axis of the planet, and also on its eccentricity. So if you look at this curve, which is the probability distribution, most of the solutions, they are for semi-major axes that are below 10 astronomical units. So now if you use the upper limits sets from the radial velocity measurements that Anne-Marie Lagrange collected in 2012, you end up with an independent upper limit on the mass of the planet, which is 15.5 Jupiter masses. And if you take the maximum of the probability distribution, which is peaking around 9 AU, then you can say that your planet has an upper limit on its mass that is around 12 Jupiter masses. So I advise you to take a look at the poster of Anne-Marie, where all these results are nicely presented. So these kind of constraints, they are quite unique actually. This is the only object for which we have such a constraints on the mass, and it enables us to discuss which kinds of evolutionary tracks are able to reproduce the observations. So we compared first, we first tried to redetermine the mass of the planet using hot start evolutionary tracks and our determine effective temperature and luminosity for the planet. So the new properties we are deriving show us that the object has to be in the planetary mass range typically. So these tracks are giving masses that respect these independent constraints on the mass of the object. Using the cold start model, so the other extreme hypothesis where all the gravitational energy at the formation of the object is lost at an accretion shock. Using this kind of tracks, we are not able to predict masses that are in agreement with the observations. But as you know, these two kind of tracks, they are the kind of extreme in terms of initial conditions that you can consider for your planet. And there is probably a continuum of solution. The impact of the initial conditions on the different way the object will cool down has now been explored using the warm start models. So in these models, the models actually do not consider all the object form, but it sets an additional 3 parameters, which is the initial entropy. And for a given initial entropy and an object mass, you are going to have a given cooling curve. So there have been actually 2 sets of models, which are the one of Spiegel and Burrows, and the one of Marlowe and Cumming. And we use the ones of Spiegel and Burrows that has been published first. And what you have to remember is that these models will predict you for a given age different luminosities for different masses and initial entropies. And that the luminosities will tend to increase with the mass and the initial entropy. So this is, what we did is that we first took the different predictions of these models for the different mass and initial entropies, and we reported the measurement we got for beta Pictoris for a system age of 12 million years. We did the same actually for the other possible ages for the system and the other possible luminosities for beta Pictoris B, so for an age of 20 million years, and for another age, which is the lower limit of 8 million years. And if you report these different constraints, it define a range in a space in the parameter space mass initial entropy that where the predictions of the warm start models are reproducing the observables. And you can do the same actually for the effective temperature of the object, and also for different photometric bands that for different absolute magnitudes that we measured for beta Pictoris. And you can also report. This is very nice because this is the only thing. This is the only company where you can really do that with a high confidence level. You can report the upper limits on the dynamical mass of beta Pictoris and exclude already part of this parameter space allowed for beta Pictoris. And what you see is that the initial entropy of the planet has to be intermediate by between the initial entropy adopted for cold start evolutionary models and hot start evolutionary models. Actually, we did this exercise for using as input of the models the effective temperature, the luminosity, and the different photometric bands. And we also find that using these models, so if you look at this portion of the diagrams, you can see that the mass has to be higher than 8 Jupiter masses. Actually, combining all the constraints we have, all the observables, we're able to say that for the given a wide range of possible initial conditions, the mass of the planet has to be higher, it has to be more massive than 6 Jupiter masses. And at the same time, you have an upper limits coming from the radial velocity. This is the most conservative value for the dynamical mass. And then you can restrain an interesting, you can give an interesting mass constraints on the mass of the planet. And you can use this and the semi-major axis that we got from the astrometry to discuss the formation scenario of beta Pictoris. So actually in the previous paper we made the hypothesis that the planet could have been formed by co-accretion or disk instability. So here we just tried to use this time formation models designed for the star and to try to revise this kind of claim. So what we did is we first used the models, the disk instability models of Hubert-Claude. So these models enables you to know where for a given star at a given mass you are able to form fragments that will be also able to cool down and form giant planets. So this corresponds to this zone in these diagrams, where here you have the semi-major axis and the fragment mass. And you can report on this diagram the location of beta Pictoris, which is here. And as you can see, the planet, according to these formation models of Hubert-Claude, it cannot have been formed in situ, so it would require a large amount of inward migrations to explain its current properties and semi-major axis. So you might think that maybe to prevent the planet from growing too much, maybe the planet could have opened a gap during its formation process. We explored the hypothesis of a formation by co-accretion, this time using the population synthesis models of Christophe Mordassini. So we used the models for 1.7 solar mass star at solar metallicity. So the metallicity of beta Pictoris is relatively well known. We made the hypothesis that the planets form one by one in the disk. They migrate through type 1 and type 2 migrations, and they do not open the gap. And as you can see, the distribution of synthetic planets, in this distribution, you can see that some of the planets here have the properties, the observed properties of the planet. But as you can see also that the beta Pictoris is lying in the envelope of this distribution, so it's probably a kind of outlier. So in summary, we got from this data the first J, H, and M prime band detections of beta Pictoris B, which enable to complete the spectral energy distribution of the planet. These data were used as input of atmospheric models that enable to say that there is a high content of dust in the atmosphere of this object. With the models and the empirical analysis also enable us to derive at a high accuracy the bolometric luminosity of the object and its effective temperature. And then we apply different models to try to get a lower limit on the mass of the planets, and we also use the astrometry to derive an upper limit on the mass of the planet. And based on this, we rediscuss the formation processes using dedicated formation models, and we find that, well, the two processes are still possible, disk instability and corrections, but they need to be a bit fine-tuned to explain the properties of the object. So the results are presented in a paper which is actually on AstroPH, so please take a look and come to find me if you have some questions. I'd like just to show you some prospects. Okay, so we actually obtained a L-band spectrum of the planet, so stay tuned. There should be some new information coming out soon on AstroPH. And another prospect that is interesting is the discovery of other companions that can help us to sketch a bit more the formation process of beta peak. And actually, I think most of you saw on AstroPH this morning, we announced, this Monday, we announced the probable detection of massive planets in around 8 type stars, which has an age of around 17 million years, so almost compatible with the age of beta peak. So thank you for your attention.
Thank you. Are there any questions for Mickael? Yes.
Hi. What's the probability that the planet will transit, and when will it be transiting?
So I'm not sure I can really answer this question right now. Actually, the poster of Anne-Marie, in the poster of Anne-Marie, the orbits are still compatible with the transit events of 1981. I think, as far as I remember, the transits, the predictions are for a next transit around 2019. But I'm not sure we can really give a probability at this time. I mean, the orbital constraints are too, not known at a sufficient accuracy to do such a job.
This is actually just a very quick comment on your on the bit about disk instability. So we actually did some work where we were looking at migration of planets in gravitationally unstable disks, and we do actually find that they migrate pretty rapidly.
Yeah.
I don't know whether it's too rapid for this or not, but it's certainly a possibility. That
yeah, exactly. I mean, well, this is why I mentioned it's the paper of Zhu and Mickael, and there have been a lot of work actually claiming that the timescales are, I think, 10,000 years, so it's very short. You're right, but we'd be a bit cautious because, as we saw from, for instance, for the population synthesis models of Christophe Mordassini, the migration efficiency is not very well known so far. So we have to be a bit careful, I think. Yeah.
It's the first flux calibrated detection at M prime. I had the first detection at M prime. But the question I had is, Rome was not built in a day, and neither was Beta Pic B. So how do your conclusions about the luminosity and the mass, and also the initial entropy change if you allow the planet to have been formed after 3 to 5 million years?
Yeah, so I think it relates to your paper that you posted on AstroPH, so okay, I prepared a slide actually. Okay, so going to be a bit tough. So actually, this paper is presenting a new detection at 3.1 micron. Tain reanalyzed the data at the other wavelengths that we got and that he got from Gemini. And actually, your hypothesis is that the planets might have been formed a bit later compared to the age of the star. Well, it's a possibility, of course. I like this picture, but you base your hypothesis on the estimation of the radius of the object that you derive, you fitting the actual SCD with atmospheric models and using a dilution factor. Actually, I refrained from doing this in my paper. I did it actually, but I refrained from using this information to discuss anything about the age of the object because I believe that atmospheric models are not well calibrated right now to allow for such an analysis. I think actually it would be nice to use different models like the one of Fortney and try to see if we are able to, what range of radius we are deriving for the object. But right now I think it's a bit too early to do such a thing. Thank you.
Hi, do you have a clear detection that beta peak B is about to go back toward the star? Did you see it decelerating to 3 sigma?
Sorry, do you see?
Do you see beta picturus B decelerating so it's about to go back toward the star?
Actually, I don't know. I don't think so. Actually, it's at the quadrature. We know it's probably at the quadrature, so it's at a very favorable position for further spectroscopic monitoring. But I don't remember exactly what are the other constraints that Anne-Marie got from the very last data points. I advise you to take a look at our poster. I don't want to say mistakes.
Any more questions? There, sorry, right in front. Yes, okay.
Thanks. So two hopefully quick questions. First, your plot for the simulated planets of mass and separation. Just out of curiosity, if you take those simulated planets and you have an idea of their age, how do if you plug them into evolutionary models, how does that compare with beta pic itself?
So actually, we tried to do that with the new code of Christophe Mordassini, which coupled the formation of these planets and their evolution. And Christophe is making two hypotheses for the accretion shock. He is saying that the accretion shock is even fully efficient, so you have a cold start or you have a hot start. And both the cold start and the hot start hypotheses are working for beta picturis, so you can form the planet with the observed luminosity and temperature for both hypotheses. The idea is that actually beyond this problems with the efficiency of the accretion shock, there is other things entering the games, like the deuterium burning. There is also possibly some other energy sources, like the infall of planetesimals in the envelope, that are adding some, that are increasing the initial entropy of the planet. So that's an ongoing work, and yeah, please take a look in a few months from now when we'll have more final results. Yeah.
And I guess a second question is, what are the prospects for eventually getting a high enough resolution spectrum to do a similar analysis as Quinn Konopaki did for HR8799C for beta pic?
Yeah, I love this analysis. Actually, the spectrum is so beautiful. For beta pic, it's going to be a bit more difficult because, as you know, the planet is a bit more, it has a closer separation, the contrast is high. I think we could think about trying to get first a low resolution spectrum with sphere. It might give us some insights on the atmospheric composition of the planet. But if you want to get a high resolution spectrum, actually from the source there is no instrument that can do that. Symphony, for instance, on the VLT, which is the same kind of instrument as OSIRIS. It's limiting by persistence effect, so you cannot really use it to do these kind of things. Yeah. So we have to wait for a couple of years, I think.
Okay, let's thank Mickael again.